Now, in this lecture, we find out the length of chord CB. In the drawing, we have a semicircle. We know that the center of this semicircle is at this point, point O. Inside the semicircle, we have square DEFO, and we know that the area of this square is equal to 5 square units. Our mission is to find out the length of this chord called CB. So first of all, because of the fact that square DEFO, or that DEFO is a square, we know that all the angles inside the square are right angles. Therefore, those 4 angles are all right angles. So I write it down. This angle is a right angle. This is also a right angle. This angle is a right angle. And finally, this is also a right angle. We know that the area of this square DEFO is equal to 5 square units. The area of square DFEO is equal to 5 square units. And we know that the area of any square is the side times side, side times side, because of the fact that all the sides are equal to each other. Therefore, the area of the square is side times the side. And we know that the area equals to 5 square units. So 5 equals to side square. We'll take a root out of this equation and we'll get that one side of square DFEO equals to square root of 5 units. So all the sides of this square are equal to square root of 5 units. In the next step, we'll join points D and O together by straight line. By joining points D and O together, we actually created here a right triangle DFO. The right triangle, the green triangle DFO is a right triangle. So I'll copy the green right triangle DFO in a new page and we'll implement the Pythagoras theorem on this green right triangle. This is the right green triangle DFO that I copied from the original drawing. We'll implement the Pythagoras theorem on this right triangle, triangle DFO. So by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this specific right triangle DFO, the square of the hypotenuse is the hypotenuse is DO, therefore the square of the hypotenuse is DO square, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to DF square plus FO square. Again, according to the Pythagoras theorem, DO square equals to DF square plus FO square. So DO square, that is to say the square of the hypotenuse, equals to DF square. DF equals to the square root of 5, therefore DF square equals to the square root of 5 square plus FO square. FO also equals to the square root of 5, therefore FO square equals to the square root of 5 square. So I found out that actually DO square equals to square root of 5 square is 5 plus square root of 5 square is 5. So DO square equals to 5 plus 5, that is 10. We take root out of this equation and we get that DO equals to the square root of 10 units. So here the hypotenuse, the length of the hypotenuse is square root of 10 units. Well, DO equals to the square root of 10 units. DO is the hypotenuse of the green triangle, but DO, it is also the radius of this semicircle. Why? Because of the fact that DO starts from point O, that is the center of the semicircle, and ends at point D, that is a point of the semicircle itself. This is exactly the definition of a radius. So we can write down that DO is the radius of the semicircle that is equal to the square root of 10 units. So the radius of the semicircle equals to the square root of 10 units. What is the definition of OB? Line segment OB, it starts from the center of the semicircle, that is to say from point O, and ends at point B. That is the point of the semicircle itself. Therefore, OB is the radius of the semicircle, that is equal to the square root of 10 units. Likewise, if you focus on AO, it starts from the center of the semicircle, that is to say from point O, and ends at point A, that is the point of the semicircle itself. Therefore, AO, it is also the radius of the semicircle, that is equal to the square root of 10 units. In the next step, I will present to you a new rule, and we will implement the new rule in this drawing. In our drawing, actually, the new rule is rule number 1. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. Repeat again, according to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. What is the meaning of this rule? Actually, the meaning of this rule is that if we have, for example, the straight line AB, this is a straight line, and we have this point, that is point K. This side KL. So, if you focus on the upper side of the straight line AB at point K, according to this rule, rule number 1, the sum of the angles in the upper side of AB at point K must be equal to 180 degrees. That is to say, the sum of those two angles, this angle plus this angle, in total, they must be equal to 180 degrees. Or, this angle is angle AKL plus this angle, that is actually angle LKB. In total, the sum of those two angles must be equal to 180 degrees according to this rule, rule number 1. So one side of this straight line AB is the upper side. The same thing is true about the lower side. That is to say, the sum of the angles in the lower side of this straight line AB must be equal to 180 degrees. That is to say, this angle equals to 180 degrees also. So we actually can implement rule number 1 in our drawing. Why? Because in our drawing we have this semicircle. AB is the diameter of this semicircle. So AB is the diameter of the semicircle. It is absolutely a straight line. So if we focus on the upper side of the straight line AB at point O, here the sum of those two angles must be equal to 180 degrees according to this rule, rule number 1. So which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, actually the missing angle must be equal to 90 degrees. In order to complete the sum of the angles in the upper side of AB at point O to 180 degrees, the missing angle must be equal to 180 degrees. That is to say, angle EOB equals to 90 degrees. And because of the fact that angle EOB equals to 90 degrees, it means that triangle EOB is a right triangle. The pink triangle EOB is a right triangle. Therefore, we can implement the Pythagoras theorem on this right pink triangle EOB. So we'll copy the right pink triangle in a new page and we'll implement the Pythagoras theorem on this pink triangle. Side OB is twice as long as side EB, so must be here. So actually, this is triangle EOB that I copied from the original drawing. This pink triangle. We know that the perpendicular EO equals to square root of 5 units and the perpendicular OB equals to the square root of 10 units. Our mission is to find out the length of the hypotenuse. We'll find out the length of the hypotenuse EB by implementing the Pythagoras theorem on this right triangle EOB. So in the right triangle EOB, by PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of this right triangle is EB, therefore the square of the hypotenuse is EB squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to EO squared plus OB squared. And again, according to the Pythagoras theorem, in the right triangle EOB, EB squared equals to EO squared plus OB squared. So EB squared equals to EO squared. EO equals to the square root of 5, therefore EO squared equals to the square root of 5 squared plus OB squared. OB equals to the square root of 10, therefore OB squared equals to the square root of 10 squared. So I found out actually that EB squared, that is the square of the hypotenuse, EB, equals to the square root of 5 squared, that is 5, plus the square root of 10 squared is 10. So in conclusion, I found out that EB squared equals to 5 plus 10, that is 15. We take the root out of this equation, and we find out that actually EB the hypotenuse EB equals to square root of 15 units in its length. So here EB equals to the square root of 15 units. You can write down here also in the original drawing that EB equals to the square root of 15 units. Our mission is to find out the length of chord CB. We already found out that EB equals to square root of 15 units. The only thing that is left to find is to find out the length of this line segment CE. In order to find out the length of line segment CE, we'll make a construction. We'll actually complete this semicircle to a circle. The first step. We actually completed the semicircle to a circle. In the next step, we'll extend side EO on both sides, in the upper side and in the lower side. Here we'll extend OE in the upper side by a straight line until it touches the circle. At this point, we'll define the touching point of the extended OE, and the circle is point M. In the next step, we will extend side EO into the lower side by a straight line until it touches the circle, and we will define the touching point of the extended EO and the circle as point N. So what is actually line segment ON? Line segment ON starts from point O, that is the center of the circle and the center of the semicircle also, and ends at point N, that is the point on the circle itself. This is exactly the definition of a radius. That is to say, ON is the radius of this circle and semicircle that is equal to the square root of 10 units. Okay? And what is the length of EO? The length of EO is equal to 5 units. The length of ON is equal to 10 units. Therefore, the length of EN equals to EO plus ON. Again, EN equals to EO plus ON. Repeat again. EN equals to EO plus ON. That is to say, EN equals to EO equals to the square root of 5 units plus ON that is equal to the square root of 10 units. So in conclusion, we found out that EN equals to the square root of 10 units plus square root of 5 units. Okay? Here EN equals to the square root of 10 units plus the square root of 5 units. What is the length of line segment ME? The length of line segment ME, it is very easy to see from the drawing that ME equals to MO minus EO. Again, ME equals to MO minus EO. I write it down. The length of line segment ME is equals to MO minus EO. So ME equals to MO. MO is the radius of the semicircle because of the fact that it starts from the center of the semicircle and ends at point M, that is a point on the semicircle itself. Therefore, MO is the radius of the semicircle that is equal to the square root of 10 units minus EO. We have already found out that EO is one side of square DEFO that is equal to the square root of 5 units. So in conclusion, we found out that ME equals to the square root of 10 units minus square root of 5 units. Okay. While ON equals to the square root of 10 units and EB equals to the square root of 15 units. In the next step, I will present to you a new rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2 is true in any circle. So in any circle, so here I will draw a circle that could be any circle. In this circle we have chord AB. This is chord AB. That intersects with chord CD. This is chord CD. So chord AB intersects with chord CD. At this point, we define the intersection point between the two chords as point O. So we can write down that if chord AB intersects with chord CD at point O, then the following equation will be true. AO times OB equals to CO times OD. I repeat again. If chord AB intersects with chord CD at point O, then AO times OB equals to CO times OB. Again, AO times OB equals to CO times OB. Actually, we can implement this rule number 2 in our drawing. Why? Because in our drawing we have chord MN. This is chord MN. That intersects with chord CB. This is chord CB at point E. Point E is the intersection point between the two chords. Therefore, we can implement here rule number 2 because we have two chords that intersect with each other. Therefore, according to rule number 2, we'll get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. So I'll copy the two chords that intersect with each other in a new page, and we'll implement rule number 2 on those two chords that intersect with each other. So actually have two chords that intersect with each other. For that reason, we can implement here rule number 2. You can see from the drawing that chord MN passes through the center of the circle, that is to say from point O. So we have here chord MN. This is chord MN that intersects with chord CB. This is chord CB at point E. Intersects with chord CB. At point E. The intersection point between the two chords is at point E. So I write it down. Now our original drawing. Chord MN intersects with chord CB at point O, at point E. Again, chord MN intersects with chord CB at point E. Point E is the intersection point between the two chords. Okay. Therefore, according to rule number 2, we will get that ME times EN equals to CE times EB. CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5, so I write it down. We have already found out that En equals to the square root of 10 plus square root of 5. And we have already found out that the length of EB, line segment EB, equals to the square root of 15 units. So we can put the data inside this equation and we'll find out the missing line segment CE. So ME equals to the square root of 10 minus square root of 5 times En. En equals to the square root of 10 plus square root of 5, and it is equal to CE is the missing line segment, so we leave it as it is, times EB. We have already found out that EB equals to the square root of 15 units. So we found out that according to rule number 2, square root of 10 minus square root of 5 times square root of 10 plus square root of 5 equals to CE times square root of 15. You can write down here that square root of 10 plus square root of 5 times square root of 10 minus square root of 5 equals to CE times square root of 15. We find out the value of this expression, square root of 10 plus square root of 5 times square root of 10 minus square root of 5. According to the algebraic identity, it states that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to square root of 10 and B equals to the square root of 5, and A plus B times A minus B equals to A squared minus B squared. That is to say, in our expression, square root of 10 plus 5 times square root of 10 minus 5, it is equal to A squared plus minus B squared. A squared equals to A equals to square root of 10, therefore A squared equals to the square root of 10 squared, that is 10 minus B squared. B equals to square root of 5, therefore B squared equals to the square root of 5 squared, that is 5. And it is equals to A squared, it is equals to, here in this equation, square root of 10 minus square root of 5 times square root of 10 plus square root of 5 equals to CE times square root of 15. Okay, so 10 minus 5 is 5, so 5 equals to CE times square root of 15. Found out that 5 equals to CE times square root of 15. We divide this equation by square root of 15. And so here CE equals to 5 over square root of 15. We found out that CE equals to 5 over square root of 15. We are actually looking for the length of this chord called CB. It is very easy to see from the drawing that CB equals to CE plus CB. Again, CB equals to CE plus CB. So I write it down. From the drawing, it is very easy to see that CB equals to CE plus EB. We just right now found out that CE equals to 5 over square root of 15, and we have already found out that EB equals to the square root of 15. So in conclusion, the answer to our question is that CB equals to 5 over square root of 15 plus square root of 15. In order to have a common factor in 5 over square root of 15, we will multiply square root of 15 by square root of 15, and then we will divide it by square root of 15. Square root of 15 over square root of 15 is 1, so we actually multiply square root of 15 by 1, so we change nothing. Therefore, it is allowable. So, in this way, we get a common factor with 5 over square root of 15. So, actually, CB equals to 5 over square root of 15 plus square root of 15 times square root of 15 over square root of 15. So we actually found out that CB equals to 5 plus square root of 15 times square root of 15 is 15. In the denominator we have square root of 15. In conclusion, we found out that CB equals to 5 plus 15 over square root of 15. So I write it down. We found out that CB equals to 5 plus 15 is 20 over square root of 15. Here we will multiply this expression by square root of 15 and then we will divide it by square root of 15 in order to eliminate the square root that is in the denominator. So we get here that CB equals to 20 over square root of 15. Here we will multiply this expression by square root of 15, then we divide it by square root of 15. So actually found out that CB equals to, in the numerator we have 20 times square root of 15 over square root of 15 times square root of 15 is 15. Here we will divide both the numerator and the denominator of this expression by 5. So in the numerator we have 20 over 5 is 4. So in total in the numerator we have 4 times square root of 15. In the denominator we have 15. 15 over 5 is 3. So in conclusion, we found out that the value of chord CB, the chord that we are looking for, this chord CB, equals to either 5 times square root of 15 over 4, or in terms of numbers, it is equals to 5.164 units. I repeat again, we actually found out that the length of this chord called CB, the chord that we are looking for, equals to either 4 times square root of 15 over 3, or in terms of numbers, the length of CB equals to 5.164 units. In the next step, I will summarize the lecture. Actually, in the original drawing, we had the semicircle. You know that the center of this semicircle is at this point O. Inside this semicircle, we have a square DEFO. We know that the area of this square equals to 5 square units. And our mission is to find out the length of this chord called CB. So, first of all, because of the fact that DEFO is a square, we know that all the angles inside the square are right angles. So those 4 angles that is inside square DEFO, they are all right angles. That is to say they are equal to 90 degrees. Those 4 angles, they are all equal to 90 degrees. And we know that the area of this square DEFO equals to 5 square units. And we know that the area of any square equals to one side times another side. That is actually, if this is a square, the area of this square equals to the length times the width. but because of the fact that the length and the width have the same length, the width and the length of this square is the same, therefore the length times the width equals to the side times the side. That is the area of any square, and especially of square DEFO. What we know, it is given us in the question that the length of square DEFO equals to 5 square units. Therefore, 5 equals to side times side. 5 equals to side times side is the side squared. We took a root out of this equation and we found out that the length of one side of square DEFO equals to square root of 5 units. So that is to say here, all the sides of this square DEFO are equal to square root of 5 units. In the next step, we join points D and O together by a straight line. By joining points D and O, we created here the green right triangle DFO, and then we implemented the Pythagoras theorem on the green triangle DFO. So I copied the right green triangle in this new page. This is the right triangle DFO. We have already found out that DF equals to FO. They are both the sides of the square, therefore they are equal to square root of 5 units. And the only missing side is the hypotenuse DO, so we can find out the length of the hypotenuse DO by implementing the Pythagoras theorem on this right triangle, triangle D of O. So according to the Pythagoras theorem, PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle DFO is DO, therefore the square of the hypotenuse is DO square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to DF square plus FO square. So in conclusion, we found out that according to Pythagoras theorem in the right triangle DFO, DO square equals to DF square plus FO square. So DO square equals to DF square. DF equals to the square root of 5, therefore DF square equals to the square root of 5 square plus FO square. FO also equals to the square root of 5, therefore FO square equals to square root of 5 square. So we found out that DO square equals to the square root of 5, that is square root of 5 square, that is 5, plus square root of 5 square, it is also 5. So in conclusion, we found out that DO square equals to 5 plus 5, that is 10. DO square equals to 10. We took a root out of this equation and found out that DO equals to the square root of 10 units. So the hypotenuse DO equals to the square root of 10 units. Here, the hypotenuse DO of the green right triangle DFO equals to the square root of 10 units. DO is the hypotenuse of the green right triangle DFO, but DO, it is very easy to say that DO starts from point O, that is the center of the semicircle, and ends at point D, that is the point on the semicircle itself. This is exactly the definition of a radius. Therefore, DO is the radius of this semicircle. DO is the radius of the semicircle, and we found out that DO equals to the square root of 10 units. Therefore, the radius of this semicircle equals to the square root of 10 units. OB is also the radius of the semicircle because of the fact that it starts from the center of the semicircle and ends at point B, that is a point on the semicircle itself. Therefore, it is also equal to the square root of 10 units. Likewise, OA, it is also the radius of the semicircle. For the same reason, it starts from the center of the semicircle, that is to say from point O, and that's at point A, that is a point on the semicircle itself. Therefore, OA is the radius of the semicircle, that is equal to the square root of 10 units. Okay? So here, I presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, that is actually Rule number 1, according to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So if AB is a straight line, and we have this point K on AB, and we have side LK, so if we focus on the upper side of the straight line AB, this is the upper side of the straight line AB at point K. In the upper side of AB at point K, the sum of the angles must be equal to 180 degrees according to this rule, rule number 1. That is to say, the sum of those two angles must be equal to 180 degrees. This angle is angle AKL. So angle AKL plus angle LKB, in total the sum of those two angles must be equal to 180 degrees according to this rule, rule number 1. The same thing is true, so the sum of the angles on one side. The sum of the angles on the upper side of this straight line AB is equal to 180 degrees. Therefore, for the same reason, the sum of the angles in the lower side, that is to say, if we focus on the lower side of the straight line AB at point K, here this angle must be equal also to 180 degrees. So we can implement rule number 1 in our drawing. Why? Because in our drawing we have this is a semicircle, and AB is the diameter of this semicircle. AB is the diameter of the semicircle, it is absolutely a straight line. So AB is a straight line, and if we focus on the upper side of AB, this is the upper side of AB at point O, here the sum of the angles must be equal to 180 degrees according to rule number 1. Which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees. This is one angle of the square, plus the missing angle. In total, they must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees, rule number 1. That is to say, 90 degrees plus the missing angle, in total, they must be equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees also. In order to complete the sum of the angles on the upper side of AB at point O to 180 degrees, the missing angle must be equal also to 90 degrees. That is to say, we found out that this angle, it is a right angle, or angle EOB equals to 90 degrees. If angle EOB equals to 90 degrees, it means that the pink triangle EOB is a right triangle. If triangle EOB is a right triangle, we can implement the Pythagoras theorem on this right pink triangle EOB. So I copied the right triangle EOB in a new page and we implemented the Pythagoras theorem on this right triangle. This is the right triangle, the right pink triangle EOB that I copied from the original drawing. We have already found out that EO equals to the square root of 5 units. OB, it is actually the radius of the semicircle that is equal to square root of 10 units. We found out that according to rule number 1, this angle equals to 90 degrees. The only missing thing is the hypotenuse EB. We can implement the Pythagoras theorem by PT, the equation for Pythagoras theorem, on this right triangle, triangle EOB. According to the Pythagoras theorem, on this right triangle EOB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. Okay, so EB squared, that is the square of the hypotenuse, equals to EO squared. EO equals to square root of 5, therefore EO squared equals to the square root of 5 squared, plus OB squared. OB equals to the square root of 10, therefore OB squared equals to the square root of 10 squared. So in conclusion, we found out that according to the Pythagoras theorem, EB squared equals to the square root of 5 squared, plus square root of 10 squared. that is to say EB square equals to the square root of 5 square is 5, plus square root of 10 square is 10. So in conclusion, we found out that EB square equals to 5 plus 10. 5 plus 10 is 15, therefore EB square equals to 15. We took a root out of this equation and we found out that EB equals to the square root of 15 units. Here the hypotenuse EB, the length of the hypotenuse EB equals to the square root of 15 units. Okay, so here we can write down that this line segment EB equals to the square root of 15 units. That is actually also the hypotenuse of the right pink triangle EOB. So our mission is to find out the length of this chord called CB. We have already found out that EB equals to the square root of 15 units, therefore the only thing that is left to find is to find out the length of line segment CE. In order to find out the length of this line segment CE, we did actually a construction. We completed this semicircle to a circle. In the next step, we extended side EO on both sides. We extended line segment EO on both sides. We extended line segment OE into the upper side by a straight line until it touches the circle at point M. Point M is the touching point between the extended OE and this circle. Then we extended the line segment EO by a straight line towards the lower side. So we extended line segment EO by a straight line until it touches the circle at point N. Point N is the touching point of the extended line segment EO and the circle. Okay, so what is actually line segment ON? What is the definition of line segment ON? Line segment ON starts from point O, that is the center of the circle, and ends at point N, that is the point on the circle itself. This is exactly the definition of a radius. Therefore, ON is the radius of this circle that is equal to square root of 10 units, because of the fact that the radius of the circle and the radius of the semicircle, they have the same value, that is actually equals to square root of 10 units. So the radius of this circle equals to the square root of 10 units, that is to say ON equals to the square root of 10 units. Then, what is the length of line segment NE? The length of this line segment NE, it's very easy to see that the length of NE or EN equals to EO plus ON. Again, EN equals to EO plus ON. EN equals to EO plus ON. That is to say, EN equals to EO. We already found that EO equals to the square root of 5 units. It's actually one side of the square plus NO. We just right now found out that EO is the radius of the semicircle and the circle, that is equal to the square root of 10 units. So in conclusion, we found out that EN equals to the square root of 5 units plus square root of 10 units, so EN equals to the square root of 10 units plus square root of 5 units. In the next step, we found out the length of this line segment ME. From the drawing, it is very easy to see that ME equals to MO minus OE. Again, ME equals to MO minus EO. MO minus EO equals to ME. Again, ME equals to MO minus OE or EO is the same. That is to say, ME equals to MO. MO is the radius of the semicircle, that is equal to the square root of 10 units, minus OE. OE is one side of the square, that is equal to the square root of 5 units. So in conclusion, we found out that ME, that is equal to MO minus EO, equals to the square root of 10 units minus square root of 5 units, and we have already found out that EN equals to the square root of 10 units plus square root of 5 units, and we have already found out that EB equals to the square root of 15 units. In the next step, I presented to you a new rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, rule number 2 is true in any circle. So if we have this circle, that could be any circle, and chord AB, this is chord AB that intersects with chord CB, the red line is called CB, chord AB intersects with chord CB at point O. Point O is the intersection point between the two chords. Okay, so if we have in a circle two chords that intersect with each other internally, like in this drawing, then the following equation is true. AO times OB equals to CO times OB. Again, AO times OB equals to CO times OB. Okay, we actually can implement this rule number 2 in our drawing. Why? Because in our drawing we have chord MN, this is chord MN, that intersects with chord CB, this is chord CB at point E. Point E is the intersection point between the two chords, therefore according to rule number 2, we'll get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. So I actually copied the two chords that are intersect with each other in a new page, and we implemented rule number 2 and our drawing. Again, I copied it here. You can see here that chord MN, this is chord MN that intersects with chord CB, this is chord CB, it's point E. Therefore, we can implement here rule number 2, because we have here two chords that intersect with each other internally, inside the circle. So, according to rule number 2, ME times EN equals to CE times EB. Again, according to rule number 2, ME times EN equals to CE times EB. Okay, again, chord MN intersects with chord CB at point E. Therefore, according to rule number 2, ME times ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. We have already found out that M equals to the square root of 10 and square root of 5. We have already found out that En equals to the square root of 10 plus square root of 5. And we have already found out that EB equals to the square root of 15. The only missing line segment is line segment CE. So we can put the data inside the equation, this equation that is true according to rule number 2. And we find out the missing line segment CE. ME equals to the square root of 10 minus square root of 5. En equals to the square root of 10 plus square root of 5. CE is the missing line segment, so we leave it as it is, times EB. EB equals to the square root of 15. So we have here square root of 10 minus square root of 5 times square root of 10 plus square root of 5, or we can write it square root of 10 plus square root of 5 times square root of 10 minus square root of 5. We can change the order here. It doesn't matter at all, because A times B equals to B times A. So what is the value of this expression? Square root of 10 plus square root of 5 equals to square root of 10 minus square root of 5. Actually, we have algebraic identity. According to the algebraic identity, that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to square root of 10, B equals to the square root of 5. So this expression equals to A squared minus B squared. So if A equals to square root of 10, therefore A squared will be equals to 10. If B equals to square root of 5, B equals to square root of 5, therefore B squared equals to 5. So in conclusion, we found out that according to the algebraic identity, A plus B times A minus B equals to A squared minus B squared. Here, A squared minus B squared in our specific expression equals to 10 minus 5. Okay, so in total, this expression equals to 10 minus 5. And we have this equation that we found according to rule number 2. it is equals to, this expression equals to CE times square root of 15. It is equals to CE times square root of 15. 10 minus 5 is 5, so in conclusion we found out that 5 equals to CE times square root of 15. Here we divided this equation by square root of 15 and we found out that CE equals to 5 over square root of 15. Okay, so here we actually found out that the missing line segment CE equals to 5 over square root of 15. Okay, we can write here that CE equals to 5 over square root of 15. And what is the length of chord CB, the chord that we are looking for? It's very easy to see from the drawing that CB equals to CE plus EB. Again, CB equals to CE plus EB. Okay. Here, CB, the length of the chord that we are looking for, CB equals to CE plus EB. We have already found out that CE equals to 5 over square root of 15 and EB equals to square root of 15. So the answer to the question is that the length of the chord that we are looking for, that is to say the length of this chord, CB equals to 5 over square root of 15 plus square root of 15. Here we simplified this expression. Why? Because we don't want a square root in the denominator. Okay? In order to eliminate the square root in the denominator here, we multiplied square root of 15 by square root of 15 and then we divided by square root of 15 in order that this expression will have a common factor with this expression. Okay, so we have here 5 over square root of 15. Again, we multiplied square root of 15 by square root of 15 and then we divided by square root of 15. We actually multiplied square root of 15 by 1, so we change nothing. Therefore, it is allowable. So here, we got that CB equals to 5. In the numerator we have 5 plus square root of 15 times square root of 15 is 15. So in total in the numerator we have 5 plus 15. In the denominator we have square root of 15. So in conclusion we found out that CB equals to 5 plus 15 is 20 over square root of 15. Again, we don't want square root in the denominator, so we multiplied this expression by square root of 15 and then we divided by square root of 15. So the expression is 20 over square root of 15. We multiplied by square root of 15 and then we divided by square root of 15, so we change nothing. So in the numerator we have 20 times square root of 15. In the denominator we have square root of 15 times square root of 15. Square root of 15 times square root of 15 is 15. Here we divided both the numerator and the denominator of this expression by 5. 20 over 5 is 4, so in the numerator in total we have 4 times square root of 15. And in the denominator we have 15 over 5 is 3. So in conclusion we found out that the length of chord CB, this chord CB equals to either 4 times square root of 15 over 3 units, or in terms of numbers, it is equals to 5.164 units. Okay, again, the length of this chord CB equals to either 4 times square root of 15 over 3, or in terms of numbers, the length of this chord CB equals to 5.164 units. Okay, thank you very much.